So what I'm going to do in this video is show you how to undertake the axial compression of a syntactic foam using a representative volume element. And in this video, we're going to show you not only how to set up the model, but also how to generate the stress strain plot for this kind of analysis. And finally, we also extract effective properties. If you're interested in this, then sit back and relax as we get started with this video. So the kind of material that we're studying here is this, which basically is a syntactic foam, and the microstructure sort of would look like this. So you essentially get the spheres that are microspheres that are distributed within a matrix bulk. The reference paper that we're going to use to drive what we are doing would be this paper on micromechanical modeling of a syntactic foam, published by Caroline in 2020. Here we're going to use it to extract the properties of the material that we're going to be studying. There are 3 steps for what we'll be doing here. The first step is to create the virtual domain, the geometry of the problem, and then the second step is how to apply a boundary condition as well as the load on the system, and the third step is to actually plot the stress strain data and generate the effective properties that is relevant for this study. So let's look at the first step. The first step is based on the creation of the virtual domain, and our domain will look like this. So this is a typical representative volume element of a syntactic foam, and it's showing clearly within here. So these are the microspheres with them being extracted and cut off, and there are some internal, there are some on the edges. The length, width and height, it's a cubic system, so with length of 8 micron all side, and the microspheres have a dimension of 30 micron outward, an outside diameter of 30 microns with a very small wall thickness of 1 micron. I've actually done a detailed YouTube video, which you can see here, that explains in detail of how to actually generate this RVE, this domain. And so I do encourage you to go and have a look at that so that you can create this virtual domain for yourself before you continue with the remainder of this video. So the material model that we're going to use, the material parameters for this syntactic foam would have a matrix with properties that are written this way, and the microspheres with also properties that are written this way. I've taken those materials from, again, our reference paper, which is this Caroline paper of 2020. So the only thing that I've done differently here is treating the matrix as an elastoplastic material, just to keep the simulation simple. If you have a more in-depth, more complicated matrix model for your simulation, go ahead and use that. Just replace my elastoplastic model with whatever you're doing. So with all this now, we can go straight into ABAQUS so that I can show you how to set this up effectively. Okay, so here we are in ABAQUS, and if we just look at the assembly module, so it sort of gives us a picture of what we're trying to do. So we've created this model, so what we need to do is to create the material. So the first thing we need to do here is to create the material. So I'm going to call this the epoxy, and the epoxy has got an elastic behavior of 3.17 e to power 3 and 0.35 as the metrics. So the plasticity for this we know is 95 and 0. And then I'm just going to make it a little bit of post-yield behavior of 0.1. I mean, you can keep going on as you want. So that's our material. So the epoxy, the microspheres, so it's got an elastic behavior of 70 e to power 3 and 0.20. And we've got a plasticity associated with it, will be 965 and 0. Again, we'll just leave it like that. So an elastoplastic material model. So this is what we have here. So we create the sections as well. So the epoxy section will link it to the epoxy. So the microsphere section will link to the microsphere. And then we can go back to the part module to now make the linkage. So it's the synthetic RVE that we are using. So first thing we need to do is to remove some of the parts. So I'm going to I'll change it to cells. So I'll select just the matrix alone. So that leaves me with the parts there. So I can then do section assignment, double click on this, select all of that, and then click done. And so that becomes our microspheres. So I'll just have to invert the system, leaving behind what is got there. So that's the matrix. I'll select that, and then I'll make that my epoxy system. So then I resume everything, and so if I resume all and then go to the material model, it shows everything looking right in the way they need to be. Then we can mesh this system. So click on there. So I'm going to probably use 6 that is suggested for me, and then I'll select what we've got here, which will be tetrahedron. So we'll work with tetrahedron, and then we'll try and mesh. So that mesh looks good. So the second step is about how do you actually apply the boundary condition and loading on this sort of model. And what we are going to do is, this is essentially RVE that we're working with, And at the back end of that RVE, we apply, we fix it. At the bottom and on the other end, we'll fix it. And then this becomes our representative volume element. So the spaces on the other side of this system will have to be constrained according to settings. So basically for this end, we fix it in the X direction. For this, we fix it only in the Y. And for this, we fix it in the Z. So that we've got a representative volume element that looks like this with constraint in the X, Y, and Z at the faces that are hidden. So once these boundary conditions are implemented, so within the assembly module, we need to create a set of sets. So the first one is X back. So the X back, I'll rotate the system to the back and make sure that I'm selecting only faces, and then I'll switch these faces to face angle, select what we have at the back. It picks up everything, that's fine. So I could then say, okay, Y top. So I then go to the top, hover there, it selects everything. And then what we have here would be Z front. So this is Z front. So we'll select that, and then we can then turn this around and make sure we get also what we got here. So this other one will be X front. So that's this. Okay, Z back. And then finally Y base would be what we need to also extract. Okay, so if we then look at the set and make sure everything is fine, so it looks like we have all of our set properly selected. Every one of them is proper in the way they should be. So we've got 4 different sets. The next thing we need to do is to apply our Y compression load. And I'm going to use a slightly different approach. Some people will just go directly on the surface of interest and apply our loading. But I'm going to actually apply the load at a reference point. So the first thing here is to identify a reference point. So I'll probe within the model, find the reference point somewhere away from the model, and then identify that as a reference point, and then apply the compressive Y compression load on that point. However, it is not making any connection with the system of interest. So the first thing is to identify the surface of interest where I want to apply this load. In this instance, is what I've called the Y top. So it's the plane at the top end of the model, which is called Y top. And we need to find a way of kinematically connecting the reference point behavior to that Y top, so that when movement happens at the reference point, it will also be translated to the Y top. So it's almost like you have a linkage between the two. So as you attract one point, it affects the next point. And that is a kinematic constraint. That means constraining it in the X, Y, and Z direction so that it has the right kind of behavior on the system. I will explain in a moment why we need to do this. So what we're going to then do next is to think about the return node. So we're going to probe at the point. So I'll select that point to find where it is, and I'll say, okay, it tells me this is where it is. Okay, fine. I'm going to then create a reference point within the assembly module. So I go to create a reference point, and that reference point will be here, but because I don't want it to be attached directly on the system, I'll make it at 90. So we've got a reference point right there. So we have to create also a set for that. So that my reference point set. So I'll select that. So we've got a reference point attached to the system, and everything we have looks okay. So let's just go back a little bit and then see what step. So we'll create a step, which I'm going to call my loading step. Okay, and then we'll create a history variable. So reference point history output, and that reference point history output, if you continue here, we'll apply it on the set on the reference point. And I'm going to extract RF1, RF2, RF3, which are the reaction forces in X, Y, and Z, displacement 1, displacement 2, and displacement 3, which are the displacement in the X, Y, and Z. So we're going to use that to extract all of our properties. So this very first one, I'm going to rename it. I'm going to call it X compression. Okay, so we've got our X compression. So what would the boundary condition be? So the boundary condition here would be, okay, I'm going to fix the X back. So the X back ruler, initial boundary condition. So we will basically identify the set for the X back, and that would have to be constrained in the one direction. So we'll do the same thing, Y base. So the Y base, fix it in the 2 direction, and Z back, and fix that also in the 3rd direction this time around. So we've got all of that located. Then we apply our load. So our compression load, so it will have to be an initial loading step and we are going to apply it on the reference point. Okay, and it would have to be in the 2 direction to create the compressive load that we're interested in. So if you then study this, so you can see the system has a compressive load on the top. So once we've done that, the kinematic constraint equation has to drive this response. And our simple kinematic constraint equation that do this is this equation that says that you're looking at what's happening at the top of y top, in u being the displacement. So the displacement of the y top in the y direction would have to be equal to the displacement of the reference point in the y direction. And that's why I said that once you move the reference point, the y top surface should also move. And we are only constraining in the y direction for now. Okay, so we need to then transform it into a canonical equation. And that means a canonical equation is essentially an equation of constraint equation where the right hand side is consistently 0. So we'll move everything on the right to the left. So we end up with an equation that looks like this. So this is the format that we need to then bring into ABAQUS to enforce this constraint. And how do we do that? So the ABAQUS format of that canonical equation will be introduced using what you call a star equation, but I'll show you when we set up the model how you actually do this. So if you look at this case, the first variable here will have a coefficient of +1. The second variable has a coefficient of -1. So I've highlighted them in red. They are going to appear in the equation later on. The y top will still be there as the first variable, and then reference point is the second variable, and we're displacing them in the y direction, which means in the 2 material coordinate system direction. So you see again, all these things appear once we start setting up the model. So the next thing is that we need to create the kinematic constraint. So we're going to call it our constraint. It will be an equation-based constraint. And so one of the first coefficient is +1 for the u top. So the reference here would have to be the u top, so the y top, and it will be in the 2 direction. So -1 of the reference point we are working with, which is the RP set in the 2 direction, just like we stated before in the equation. So we've got a loading applied onto the system. And so that's how you apply a kinematic constraint, so that you apply loading on the system. Why am I going through all this hoop to do this? The advantage of doing that is that, of course, we could have easily gone and extracted what's happening on that surface, or even on the whole model, homogenize it. But then the variables that are generated during that, written to the history variable, will be quite excessive. ABAQUS currently will have a limit of 10,000, point variables that it can write directly to the history. And so in order to prevent that happening, I would rather just use one variable in this case, which is a reference point, track 2 things, and I will never run out of memory for this. So this is really about managing the memory of the history variables that I'm going to track subsequently. And those history variables are going to be essential in generating the stress strain data, which we will be doing next. So let's do the other cases. So if I look at the create a copy, and this time I'm going to make it y comp. So that's a y compression. So that's for the y comp. So for the x comp, everything remains the same. All we need to then do is, when we come back here to the compressive load, we know that we don't want it to be at this point. We want it to be in the compression direction, which is 2. So it's going to go backwards. So if we just study the system a bit, so it's pushing, and we have to link it to what's happening in the front. So how do we do that? So look at our constraint equation. Our constraint equation will now be on the x front, in the one direction. So we are pushing in the 1. Those are the only 2 changes that we need to make, and we are ready to see what happens. So for the third case, so we'll do the Z comp. So with the Z compression, again, 2 things we need to change: the load involved. So the load this time around, we want it to be in the 3rd axis. So I'll just copy that and go to the 3rd direction and paste it. So if you again see what we have here, so it's pushing backwards. So, and what is the face that we want to push? We want the front face, X front face. So how do we make that transition? So again, we look at our constraint equation, and we just change this to the Z front, and then it moves in the 3rd direction. So this movement here is linked to that point, and then we'll create the load for all that, and we'll see what result we're going to get. Okay, so let's look at the result. The first one is the X compression data. So if we oscillate that, so we can see, so if we look at the animation, so you can see what's happening here. So you're pushing the front end and it's moving backwards. So if I just put the 2 together, so you can see what is going on. So the front is being pushed, and the system is nicely compressing in a backward direction perfectly. So what about the Y comp? So again, a similar behavior is what you see in the Y compression. So the system is being pushed downwards and you generate a result that looks like this. And again, perfect. You could see what the fibers are, what the capsules are doing. They are being compressed. So for the Z compression, again, you get some excellent data, how the system is all being compressed. So the simulation seems to be working quite well with the microcapsules being the form as they're supposed to be. But clearly what we want to do is to be able to generate the stress strain data from this simulation. So how do we do the stress strain data here? Now, let's consider a representative volume element, a porous media, for example, in this instance, and I've identified the surfaces of this porous media. So we need a length, the original length of the porous media, the white top surface of interest in this instance. I'm going to extract reaction forces and displacement from there. Not directly on those white top like I've just explained. I'm going to be doing that from the reference point that is attached to that. So that's what we need. So from the simulation and what we write to history variable, we've got F, we've got displacement. We also have the length because this is a geometric length. We can easily measure this. What we don't have is the surface area. Why is the surface area a problem? Because it's an irregular surface area. So you've got this cut out that are not going to contribute in terms of the impact of the domain during the load extraction. So we need to calculate this irregular surface area. So I use a Python script to do this. And what the Python script will do is basically we'll find this reference surface and calculate cumulatively all the area of every of the remaining part that make up the surface. So I'm using the ABAQUS CA environment to help me to do this. Of course, you can also generate this from a CAD file if you've created your model in a CAD file. So this is sort of what the snippet of the code would look like. At the base here, it says print the surface area. So this will be written to the kernel command within ABAQUS, which will show what the surface area would be. And with those, we can then calculate the normal stress and the normal strain using the calculated surface area and also the history variable written force and displacement. So that's how we're going to generate our stress strain data, and we're going to show that right away in ABAQUS. So let's probably start with the first case, which is the X compression. So the X compression, so we'll look at the history output here. So the history output is what we're looking for. So it's the reaction force and displacement that we're looking at, and then you plot that. So once you plot that, you get the data. So we'll go to plugins, tools, Excel utilities, and this time around we're looking at the current plot. The essence is that I want to take out this information and manipulate it within Excel. So this is the data, so I'll just copy the data that we have here. So I've already prepared this Excel script, which will be available again for you to download if you want to to follow what I've done. So if I paste the data that we've copied, so it comes out into this window. So we've got a few things here. So the strain has been calculated, but we need to calculate the area. So we need to calculate the stress, which requires us to calculate the area. So this is the Python script that I referred to earlier on that we're going to use. So basically here, this is the name of the model that we're working with. So how do we find that out? So if we go to the model, so this X comp that we're working with, which is this. So this is the model name. So if I open that and I go back to the syntactic RVE is the part that we're working with. Okay, so again, I'll do that. And we're working on the X surface. So I'll just need to write the model name here and the part name. So what is the part? The part is basically what you have here. This is the part we're working with. The last thing we need to do is to find a point on the surface of interest. So I'll just click OK, point, and then I'll just select any point on the surface and click done. So what will happen is that right here, it will output the parameters that we need, the particular point of interest. So I'll come to this code and then I'll just paste it at the face reference point. So clearly the surface where X is equal to 80 microns is the X surface, and then this is some point within the model. So this code will iterate there and find the surface that meets this reference point criteria and then output the value. So all I'm going to do is I'm going to Control A to select or Control C to copy this, and then we come into ABAQUS again. Then within this kernel command window, I will now paste that. So what it will do is that at the end, it's outputted the parameters for the area. So the surface area of interest is that. So I'll copy, Control C to copy. Then go back to my Excel and paste it in that surface area. So we've got that, and everything is effectively worked out as well. So that's how we are going to generate the stress strain data. So obviously this is the length and the width. This is the surface area, and it calculates the Young's modulus, and the strength being the maximum value of that data. So everything is correct on that. So we can go and do the same for the Y compression data and the Z compression data, which is what I've done to generate these properties and the Z compression. And then finally, we're going to then compare the data. And if you compare the data, we get sort of the same sort of response in the X and Y compression. Z is slightly different, slightly stronger in the Z direction. And the main reason, if you go back to this data, so this is Z direction, so there's quite a lot of materials that are cut out from the system. So this is gone, that is gone, that is gone. And also this region is also gone. So as a result, you will expect that the cross-sectional area will be smaller. And because the cross-sectional area is smaller, so when you divide about the same reaction force on that surface, you tend to have a higher stress. So that's the explanation for why you have a slightly higher value. And this is why you probably need a bigger RVE if you're really operating on the strength of the material. So in the end, we get these effective properties for the X, the Y, and the Z, which are comparably, just around 3 point something, which is comparable across all of them. And the strength properties are similar across all of them. So what we can see here is really an effective, beautiful way to show how you can generate stress-strain data and effective properties from axial compression of a syntactic foam. Thank you for your interest in this video. Please do subscribe to this channel if you like this kind of content. And do leave me a comment of what you think about this strategy of extracting stress-strain data in the way that I've done it here. Is there a different way that you actually do this? And if you love this video and you want to see how you can actually create the virtual domain that I referred to earlier on, then look at this video. Thank you for your interest in this video, and I'll see you in the next. Bye-bye.